Okay, well, I think that's me back on now. Welcome, everyone. There we go. Let me just go a couple of things before we get on with the big day. Hey, everyone. Let's just do a bit of housekeeping. Can you all hear me? Can you all see me? It's me again. I know. Just to make sure we got everyone in the house. Good evening, everyone.
Yeah, evening, Marco. Yeah, I can see and hear you.
All right, perfect, loud and clear. So I've got good evening, David, Angus, Chantel. Good to have you back, Godson, of course. We've got Nicholas, Prince, Trinidad, Trudy, of all people, and Valentine. A good range of people I've not seen in a while. Actually, that's a lie. I saw you last week. So I have seen those who were last week with me this week. And we continue. The ball keeps rolling. It's nice to have us back. I'm feeling in a little bit of pronto last minute for a substitution. So again, apologising if you were expecting some fun and games, but I will try to make it fun and somewhat gamified. And we'll do a bit of a hands-on lab later on this evening. Yeah, nice to see you too, Trudy. It's been a minute. A couple of names who haven't quite come across yet before. I think Trinidad and a few others too, which I'm sure we'll get to know each other very soon. Just in case you don't know me, I'm Marco. I'm sort of in the background of the academy. I have been involved with some time now, and I'm sort of veering into all sort of side steps. One of which is one that I would like to share with you. That's okay with this evening, to talk about kind of offshoots of things that are a little bit far field. So this is the chance for us to go off and learn something new, or maybe touch on new technologies, which aren't all Team Orange, so to speak. One of the things I'm kind of interested in is at the moment is machine learning and all that kind of jazz, which I think would be a good point to go on and talk of. I mean, Fridays usually are this wildcard evening where we do tend to talk on machine learning and artificial intelligence. So I thought maybe this would be a good opportunity for me to flex what I do have been looking at, if that's okay. Specifically, of all things, is let me just send over something into the chat. So if you did want to follow along with my notes, if that's of interest to you, at least you have that there, which is just, a ragtag bunch of, I'll try to clear it up so you don't rely on these things as much, but we'll make the most of things as we go through, okay? Apologizing in advance. Today is going to be a little bit more technical. If that's something you're willing and able to do with me, it's going to be quite mathematical. If if you're with me, okay. Namely because largely in part, you can't talk about machine learning without how it learns, and that's maybe my take. My focus on that is going to be today. My take is that you do need to be at least comfortable with the notion of programming, or at least to think programmatically, as if to clear up your thoughts and understand how a computer computes. How it can generate and process information. If and because with machine learning it is so dense, I don't think any of us need to know this level of detail at a day-to-day level, but just for the sake of being familiar with the stuff, it's good to know how it all works. The kind of stuff I'm interested in at the moment is learning, specifically, of all things. Yeah, this morning I was at a Portuguese class learning, and this evening we're going to be learning about machine learning. If I can just find my pen, there you go. I'll put that to one side. Perfect. So, yeah, well, this is going to be, as you see, with Python as sort of the backing to this, because machine learning is largely, it's how a computer can talk. And for us to talk to a computer, we do need to have some intermediate language, right? So for us to be able to communicate with a machine, for it to learn, we need to pass in some instructions. And those instructions are going to be in some intermediate format, i.e. a programming language, a computation, a higher level order thinking that at the bottom of it all is all course ones and zeros, but we need to somehow pass on that information for it to process. So far in this class, we've seen Solita's has been talking at this at length. She's gone into great level detail as to how it solves various problems in terms of solutions already off the shelf, pre-formatted boxes in Amazon sense. But I wanted to give it some sense as to how the AI instructions, how it looks for solutions, how to satisfy certain constraints, if that's okay, in order to fulfill its way from some input point as to some output point in order to solve some kind of a problem. So our focus very much this evening is going to be on that point, on learning more specifically. So we're going to turn to this particular world, the idea of machine learning more generally, which refers to the sense of where we're not really going to be giving the computer explicit instructions. We're not going to be telling it what to do, holding its hand for it to perform a task, but rather we're going to give the computer access to the information. We're going to lead the computer's hand to say, here's the form of data or the patterns that you might learn from that, and then let the computer itself just figure it out, fundamentally look at the patterns, try to make sense of it, and try to understand that data, try to be able to perform a task on its own, very much the point. So, machine learning is now, it comes in many different forms, and it's a very, very wide open field. So today, I'm going to be focusing on, we're going to have a look at the more fundamental stuff, okay? We're going to see sort of the textbook algorithms, if you will, that are behind a lot of the different areas within machine learning. One of the most popular amongst which is this idea of supervised learning, of just learning more generally like this. Yeah, right. So with supervised learning, it is a very particular kind of task. My slides aren't all that interesting, but we will turn our attention to a couple of cool points in a minute. And it is a particular kind of a task. Okay, so with supervised learning, yeah, please share. Sorry, so I think if Dwayne, you're asking for something, means you can't look up, so I will send you. So rather, you can't traverse the early messages, so I'll just send that over again. Not a problem. There you go. Fine. Yeah, there you go. So with this kind of task, what we're doing with supervised learning is referring to the task where we give computers access to some data set. We say, hey, look at this, look at that data, and that data set itself is going to be made up of some input and some output pairs. Yeah. So what we would like the computer to do is, what we would like the AI to do is to be able to figure out then some kind of a function, some kind of function that's going to map the inputs to said outputs. Yep. So we have a whole bunch of data in the world. Generally, that consists of some kind of an input, some evidence, some information, a data set, if you will. And the computer's going to have access to that. What we would like the computer to do is, based on that input information, for it to predict what some kind of output is going to be. Okay, so input goes in, and then some kind of something comes out. Okay, what that thing is going to be is what we're trying to allow the machine to figure itself out, if you will. Okay, so machine learning is where we'll give it some data, and that computer is then going to somehow train itself here. Okay, this model starts to emerge where it begins to understand how it is that information works. How is it that those inputs and those outputs relate to one another? Ultimately, we want to have the computer figure some kind of a function out. Okay, F in that case, given those inputs, is able to get those outputs. Okay. So this is the goal. I mean, there are a couple of different tasks that you can do within supervised learning. But first and foremost, we want to figure out and get started on, I think, classification, right? So yeah, within, one of the functions we can perform is classification, where it's a problem, if you will, where I'm going to give you a whole bunch of inputs. I say, here, have those beans, and then you need to figure out some kind of a way for you to map those inputs into some discrete category, if you will. So like you can put them into different piles where you can decide what those categories really are. Again, the computer is literally just blind to the world, it's impervious to what's out there. So how does it begin to categorize things? The job of the computer then is to predict what those categories ought and are going to be. So the example we'll see later, if I give you a banknote with some money, it could be £5, it could be £10, and I'm asking you to predict for me, does this belong to the category of is it authentic? Is it real? Is it a banknote that's actually legit? Or is it counterfeit? Okay, is it fake? So you need to then categorize that input, and we want the computer to train itself to figure out, or to be able to do that calculation. Is it real or is it not real? Okay, is it a real £5 note? Is it a fake £5 note? Again, we want that to be found out by itself. Another more example, I think probably a cleaner example, is this, where in the case of weather, something that we talk about incessantly in the UK, we would like to predict somehow on a given day, is it going to rain? Yeah. Is there going to be a cloudy day, or is it going to be a rainy day on that day? And before we've seen how we could do this. It really would just give the computer all the exact probabilities for, if these are the conditions, then what's the probability of rain? Often, this is often given to us where we don't have that information. We don't really have the raw data at our fingertips, but what we do have access to is a whole bunch of aggregated data. So, okay, often in the past. So if we wanted to figure out and be able to predict something in the future, like, is it going to rain, or is it not going to rain? Is it this, or is it that? We would want to give the computer access to historical information, training data, okay, as to when it was raining versus when it wasn't raining. So that way we were able to ask the computer to say, you see the difference? This, that. Can you see the difference? Can you understand the patterns in the data? Whatever those patterns may be in the data set. It's up to the computer to figure that task out. So what might that data look like? Well, we could structure that in such a way that, just to refer to this table for a moment, okay? If I just put this to one side, where you might have something along these column names. So for any particular day going back, you could ask the weatherman as to have information like this, like today's humidity, today's air pressure, and rain. Oh, well, actually, importantly, we have a label. Something with a human that said, actually, on that particular day, it was raining, or it was not raining. Okay, so given that this and that, it was raining, it wasn't raining. So you can fill in the data with a whole bunch of data, just sample data, okay, dummy data in this case. And what makes this what we would call supervised learning exercise is that really a person has gone in, okay? What makes supervised learning supervised is that a person with eyes and ears and senses has gone in and started to label, often painstakingly, each of these different data points. Okay, they've said on this particular day, when these were the values for humidity and for pressure, that day was a rainy day, and this day was not a rainy day. And so what we would like the computer to be able to do is then to go ahead and figure out, okay, given those inputs, given the humidity and given the pressure, can the computer then predict what label should be associated with what day? Does that day look like more it's going to rain, or does it look like more a day that it's not going to rain? This is why, weather forecasts are often famously so wrong, because, they're not certain, okay? They're just with probability. And to put it a bit more mathematically, like, you can think of this as a function that takes in two inputs to a function, okay? The inputs being the data points that a computer can have access to, such as humidity, such as pressure. And then out of that then, you could write the function as being F. So function takes in as input both humidity and pressure. Sure. So the output of that function then is going to be what category comes out of this. So, what category we would ascribe those particular points to be. What label would we start to associate with that set input? Given this, what kind of pile would we put that on? Okay. So we've seen a couple of data points there. If I get this on screen, so this would be the value for humidity. Yeah, so on the sort of left of the first comma, where this value for humidity, and then let's imagine that no particular reason the colors are the way they are. Okay, and then this is going to be taken input. So for values for pressure, values for humidity, we then predict our prediction. Is it going to rain? Is it not going to rain? So as scary as the formula looks, this is just the information that we've just gathered from the world around us. We've measured on all various different days and different places on Earth probably what humidity and what pressures was. We observed whether we saw rain or not rain, again, because supervised learning, okay, we would then say, on this particular day, and this function f for function, we would like then it to be, to approximate this. So jumping forward, a bit for in the story then, now the computer, and we humans, okay, we don't really know exactly how this f function works. It's probably quite a complex thing, so what we're going to do instead is attempt to estimate it. Okay, we're going to have a bit of a guess. We would like it to come up with some sort of a hypothesis function. All right, so H hypothesis, which is going to try to approximate what F does. We want to come up with some kind of a function, H hypothesis, that will also take in the same inputs, at humidity and pressure, and then produce an output, rain or not. Is it going to rain? Is it not going to rain? And ideally, we would like those two functions to agree, to be as close as much as possible. So the goal then of supervised learning, again, with supervised learning is going to have, so the task is going to figure out, what does this H function look like? How can we begin to estimate, to hypothesize, given all this information in the world, all of this data, what category or what label should be assigned to that particular data point? So, okay, so where can we begin to do this? Well, a reasonable thing for us to do, especially in this situation, okay, so if I have two numerical values, which we just saw as being pressure and humidity, we could try to plot this on some kind of a graph. It's helpful to try to throw this on a piece of paper that has two axes, that's the x-axis and the y-axis, and in this case, we're just going to use two numerical values for now, just two numbers, okay, as input, but these same types of idea scale, just try to add more and more inputs here, and we're going to try to plot these things up on 2 dimensions. As we'll see in a second, though, you could try to imagine things in multiple dimensions, adding more and more and more. And while we humans do have trouble conceptualizing, anything beyond really 3 dimensions, at least virtually, okay, a computer has no problem at all in trying to imagine things in many, many, many more dimensions. So for a computer, each dimension is going to be some separate number. Okay, it's just going to keep track of something. All right, so it wouldn't really be unreasonable for a computer to think in maybe 10 dimensions, 100 dimensions, 1,000 dimensions in order to solve any kind of a problem. So for now, though, we've only got just 2 inputs for this. Phone is going off. Let me just put that on mute. So again, what we're going to try to do is graph along those 2 axes. Okay, so an x-axis and a y-axis, which are going to represent here the humidity, and a y-axis up top, which is going to represent the pressure. Again, just examples picked out of thin air, but again, as a way to hypothesize here, what we're going to try and do is say, let's take all of the days. Let's take all the days that were raining, okay, and then just try to plot the days that were raining up on this graph here, and let's see where they all fall on this graph. There you go. Okay, so this will be blue. Think of water. Okay, so all of the rainy days. These are all of the rainy days which you're going to put up on this graph somehow. Okay, humidity and pressure. So this somehow corresponds to this particular value for humidity and this particular value again for pressure. Okay, and we might try to do the same thing again for the days that were not raining. Red was just the color I went for, so not raining in that case. So I'll then try to take all the not rainy days and then to figure out what the values are for each of those 2 inputs. So we end up looking like this. So we go ahead and we plot the same thing on the graph as well. So here I've plotted them in red, not raining. Blue stands for a rainy day. Red stands for a not rainy day. Okay, so again, just color coordination, but this is going to be our input to our function. These are going to be the things that my computer has access to, all this input. What I would like to do then is the computer to be able to try to train a model such as that if I'm ever presented with a new input, such as something new comes through, okay, some unseen variable as yet, it doesn't yet have a label associated with it, then something like this white dot over here, then I will look then to predict, yeah, with what probability, given those values for the 2 inputs, pressure and humidity, should we classify this more as blue or a rainy day, or should we classify this more as a red dot, as a not rainy day? And this is why I'm going to invite you in the chat just to kind of look at this graphically and maybe say, what do you reckon? With more certainty. Yeah. Hey, welcome, Malcolm. Not at all. You're in the right place. Yeah, with blue. So Duane's gone for blue. I think probably overwhelmingly, just by looking at this picture more graphically, it's like, all right, well, this white dot, why does it belong? Just to get your thoughts on this. Feel free if you want to come on the mic. I'm inviting you to whatever you want to do. But what makes you want to put this onto the blue end, should we say? So what's your intuition here?
It follows a pattern.
Exactly. Well, okay. It follows a pattern.
Yeah.
What is that pattern that you've been able to pick apart?
The skew. So it's surrounded by blue. With the blue numbers, so it's following a pattern, so it's most likely blue.
Perfect. I'm really glad you said that. So it's following the pattern.
Yeah.
Go on.
You can't get random. Obviously, you're always going to get a random, but the chances are it's blue.
Chances are. Really interesting you said that. Okay, Dennis is going for the bureaucratic approach of potentially neither. I'm glad you mentioned both. Ankel's going for a interesting. I like that you've gone as a percentage, as a form of probability there. It's 100% blue, it's 20% red. So you're kind of on a level of certainty. I'm going to return back to that. I'm glad you mentioned that because, well, you're all right. First of all, it is much clearly on the blue side. You're right, yeah, Angus. Like that's what we're going to see later is how the model is able to predict anomalies, and why this is a flawed model to begin with. But just to simplify, right now, like Chantal's absolutely nailed it. It feels like it belongs more on the blue side, and I think most people probably will agree it belongs much more on the blue side because it looks like it's closer to him. Just look around you, yeah. Just turn your head and see, oh, it's blue, there's blue, there's blue, there's blue, there's blue, all this kind of blue. It's not a very formal notion, okay, but but it's a notion that we're going to formalize in just a moment, okay? Just right now, it seems to be close to this blue dot here, that blue dot there, all these other ones there, like that, okay? So there's nothing else that's really closer to else that we might say that it should be categorized as other than blue, yeah? So it should fall into the category of, I think that day is going to be rainy based on that particular input, okay? It might not be totally accurate, like Ankel says, but it's a pretty good guess. It's most likely that. All right, so what you've then nailed, so Chantal, you've described this particular kind of algorithm, actually a very popular one, okay, this is probably the most common machine learning algorithm out there, and that's known as, unsurprisingly, the nearest neighbor classification. Okay, maybe you can see why. So it's an algorithm, again, just for solving those classification types of problems. When I say classification, in your mind, I want you to think labeling, okay, what kind of pile do I, is it in that pile, is it in this pile? How do I classify that data, that input? Cool. So in the nearest neighbor classification, it's going to perform this kind of algorithm, which I'll, so what we want to do is that given the input of something, given something coming through, it's going to choose the class of the nearest data point to that input. So by class, what I'm saying here is just the category. So what's nearby, okay? Just, is it like rain or not rain? Is it fake money or is it real money? And if we choose that category of the class based on the nearest data point, we end up with the nearest neighbor classification. So again, just given all the data we've just looked at, is the nearest data a blue point or is it a red point? And depending on the answer to that question, we're able to make some sort of a judgment on that too. So we'll be able to say, yeah, I think it's going to be blue, or we're going to think, it's more likely to be red because look around. So far, so good. Yeah. All right, so let's just put that to practice. And then likewise, we can apply this to any other data point too, if we might find as well in the real world. Let's go for suddenly this one. So what do we reckon, folks? Surprise, surprise. What are we looking at with this data point? Suddenly out of nowhere, this data point comes about. Well, what's the nearest data? Kind of obvious, right? Yeah, so with that judgment, Dennis, if I asked you, which one would you then go ahead and classify this as? So the white dot at the moment, I'm just representing as the uncertain value, Mohammed was saying, as this input, given this kind of white dot, using the nearest neighbor algorithm, where would you reckon this best fits in, Mohammed? How would you classify this white dot as? Is it raining or not raining? Is it this or is it that? So just like Dennis is able to point out, just look around you, look around the room, and to follow suit. It's going to be red, right? Because look around you, all right? So things get a little bit tricky then. If we, oh, there we go. So look at this one. Now, if you start to look at a point like this white dot over there, and again, Mohammed, does that make sense? The white dot is just kind of the one we're focusing on. We've selected this one. Yeah. So the red is the nearest white dot before. Is that still the case now, Mohammed? I'm not picking on you. I'm just because I saw you, you answered to me. Yeah, no. Well, it is technically, actually, it is the closest kind of moon, should we say. Yeah. And let me ask you the same question then. Okay, should that belong as part of the category of the blue points, the rainy days? Or should the white dot belong part of the category of the red points, the not rainy days? What do you reckon, folks? So what should we go? Okay, now we start to think about it. Okay, so blue says, okay, pretty much half and half. Okay, so now nearest neighbor classification would say that the way you solve this particular problem is you look at which point is the nearest to that point. So looking here, this is where I am. I'm standing on this little moon. What's the nearest moon? Yeah, well, it's clearly red. That's my nearest thing. It's not a rainy day. Okay, red for not rainy. Therefore, according to that 3 nearest neighbor classification, I would say that this white unlabeled point should also be red. But like Chantal just rightly pointed out, it's a little bit harder than that, right? Because it should be classified as a not rainy day. But I think I follow Chantal's intuition too. It's like, there's a reasonable judgment to make here too, that actually, yeah, the closest thing is surely, rainy day, not rainy day, sorry, red. So you may as well guess that it's not a rainy day. But it's also reasonable too to look just further afield and look at the bigger picture, shall we say, and start to think of, you know what, true, the nearest point was a red day, but it's surrounded, it's so kind of encased in a whole bunch of other blue points. So again, zooming out, looking at the bigger picture now, there is potentially an argument to be made here to that point should also potentially be blue. Things get tricky. All right, so again, and only with this data, just so far, we don't really know for sure. I can't give you a firm answer. So what we've got then is some inputs coming through, something we're trying to predict. And we don't necessarily know what the output is going to be. So in this case, which one is correct is really difficult to say. But often, considering more than just one single neighbor, considering multiple neighbors in that case, can give us a better result. Okay, we get just much more of an informed decision. So we've seen one algorithm. We've seen the nearest neighbor classification. There's a variant on this, folks. And there's another thing that's also known as the, or close to that, so nearest neighbor. And there's another one around this that's called the K nearest neighbor classification. So what I'm telling you is that this is the kind of, within this family of classifications, there is one called K nearest neighbor, wherein K is just going to be some parameter, really, some number. I don't know why it's K, but some kind of thing, some number we choose, something for like basically how many neighbors are we going to look at. So we saw one nearest neighbor classification is the one we saw just now. Okay, just pick the one nearest neighbor to you and use that category off that neighbor. But again, with K nearest neighbor classification, where K might be like 3 or 5 or 7 or 1,000 or whatever it is we want to choose from, we look at the 3, 5, 7,000 different closest neighbors, and then we the closest data points to that. And then we use them. So the algorithm works a little bit differently on that case. The algorithm says, given the input, choose the most common class out of the K nearest data points to that input. So again, if we say K is 5 in that case, okay, just a number. And then let's say 3 of them are raining, and then 2 of them are not raining. So 2 of them are, 2 are red, 3 are green, blue. We'll go with the 3 instead of the blue because, each one effectively gets 1 vote, shall we say? And then that leans towards what they believe that category should be. So obviously, we're going to say that probably is a stronger gravity, shall we say? Okay. Ultimately, you choose the category that has the most votes, the biggest classes as a consequence of that. So again, this K nearest neighbor classification is pretty straightforward, I believe. I hope you're seeing this just as a variant of the one we just saw. It's pretty fine to understand intuitively. We just look at the neighbors, we look around you, and then we figure out what the answer might be. It turns out that this works really, really, really well for solving a whole bunch of problems that are used with classification. So. But not every model is going to work for every situation. Okay, it's not as simple as that. So one of the things that we're going to look at today, especially in the context of supervised machine learning, is that there are a whole bunch of there are different approaches to when it comes to machine learning. There are different algorithms for this, and then a whole different algorithms that we can apply to, each solving the same problem. So it's not a one-size-fits-all solution. If you see what I mean, like for solving some kind of a classification problem, which is what we're seeing right here, like is it in this part of that pile, where we want to take inputs and organize them into different categories, and there's no one single algorithm that's necessarily always going to be better than some other kind of algorithm. Okay, there are trade-offs to this. Some are better than others, and maybe again, depending on the data, what comes through, what kind of algorithm you're looking at, one is going to be better situated or one is going to be more relevant into trying to figure out what that information might be than other kinds of algorithms. Okay, so this is where a lot of these machine learning research points end up when smart people end up looking at this stuff at a lower level. Then trying to apply some kind of a machine learning technique onto this. You're often looking at not just one particular algorithm, but trying out a bunch of different algorithms. Okay, trying to see what works best given the situation, and seeing that then. Okay, so one such approach would be something that I love. It's called in a naive approach, at least, that it could be pretty fairly slow. It could be quite difficult for us to go through to and measure all the distance between any point, and then all the other data points that exist here. Now, there are a couple of ways that we can get around this, but there's data structures that can help make it more quickly to be able to get those neighbors. But there are also techniques that you can try to then prune some of that data. Okay, remove some of the data points that you're only really left with the most relevant data points, just to try to make it a bit easier for you. Okay. Ultimately, what we would like it to do is to come up with another way of trying to do this classification. And one such way of doing this classification was looking at what your neighboring points are. But another one we might try to do is then look at all the data points and see if we can come up with some kind of a decision boundary. Okay, and a decision boundary which is going to somehow separate, the rainy days from the not rainy days, the good from the bad in the case of 2 dimensions. Okay, and we can do that really simply. I mean, if we're trying to split the atom, put things on 2 sides, we can do that rather simply just by drawing a line. Okay, so what we want to do is then we try to find some kind of a line, try to find some visible separator, shall we say. No need for that to be blue. Just some kind of divider that divides the rainy days from the not rainy days, the blue from the red. And then we're now trying a different approach, okay? In contrast to the nearest neighbor from before, which is just going to look at the local data points around the data, the input data, and we care around that too. We're not doing that anymore. Here, what we're now going to do is try to solve something that looks like a line. So we call this thing linear regression because it looks like a line. Okay, so a linear regression algorithm is going to find some line that's going to separate two halves from one another. Yeah, so sometimes it's actually, in this case here, really simple, just to come up with some kind of a yellow line, just perfectly down the middle, just separates all the rainy days from the not rainy days. Realistically, though, you see where this is going. It's probably, this is maybe more cleaner than many actual real life examples, and often data is messy, life is messy, there are outliers, like Angus says, so there's random noise that just happens to be in the system. So what we would like to do is to then still be able to figure out then what a line might look like and where to place that line. Okay, so if you're with me so far, what we want to do then is figure out what that line's, some of that data might not always be linearly separable, linearly separable means where I can just draw a line to separate the two halves of it perfectly, but we can get as close to that as possible. So instead you might have a situation like this, where you've got, again, some rainy points over here on this side, and then some not rainy points on the left side, and there may be a line that perfectly separates one half of the inputs from the other half. Again, so this perfectly separates all the rainy days from the not rainy days. But we can still say that this line does a pretty good job, like it's mostly right. If we try to formalize this in a second, it gets a little bit harder later on when we try to say something like, this line does a pretty good job at trying to make a prediction. Okay, that's not great, but for now, if we just say we're looking for a line that does as good a job as we can do as trying to separate this category of items from another category of things. So if you're with me so far, and again, I'm looking at the chat, if you do have any questions at all, just to formalize what we're looking at here more formally, a bit more mathematically, what we want to do is come up with some kind of a function, okay, just to think about this more concretely, some way we can define this yellow line. So how can we write this down? Okay, obviously this is just an idea, and our inputs, are things like humidity, things like pressure in this case. So how can we maybe make this a bit more, how can we square this up? So again, our inputs on the left, we might call this input x1 in that case. That's just going to represent humidity. And x2, input 2, is going to represent something like pressure. So these two are inputs that we're going to provide to our machine learning algorithm in a second, so that given those two inputs, okay, given these things, we would like our model then to be able to, again, predict some kind of an output. Yeah, so we're now going to try to predict, using our hypothesis function, which we called H before, what the outputs are. Am I talking goobity-goo? Are you more or less with me? Yeah, so given these two things, which we're now kind of just, obviously we're just kind of thinking about them more in a more abstract sense, x1 and x2, given these things, what's the output like? There we go. So there you go. Our hypothesis function, which again is going to take in as inputs, these two inputs, x1 and x2, humidity and pressure in this case. You can imagine that we don't just have two inputs, we can have 3 or 4 or 5 or many, many, many different inputs. We could have this kind of thing going on much longer, should we say. But 2's fine for now. So we could have this hypothesis function, just take all of those different inputs as parameters, right? And we'll see examples of that in just a moment. So the question is now, well, what does it really do? What does this hypothesis function really achieve? Well, it really just needs to measure, like, is this data point on one side of the boundary, or is it on the other side of the boundary, given these two things? Like, does it fall on this side or does it fall on that side? How do we formalize that boundary we just saw from a moment ago? Well, again, that boundary, that linear regression, is going to be some kind of a line, some linear combination of these two input variables, and it's in this particular case. Okay, so what we try to do then is, when I say a linear combination, is to go ahead and grab these two things and then to multiply them by some kind of a number, and that's what we're now going to have to figure out. We'll generally call that number a thing called a weight. So a weight for how important, shall we say, if you can imagine, like, how weighted something is, how weighted it is, how important those variables should be in trying to determine that answer. So weigh each of those variables with some kind of a weight, and we might add something like a constant to it in a second, or we might try to make the function a little bit more different. And the result is we just need to compare then, if it actually is those two, is it greater than 0 or is it less than 0? Does it belong on one side of the field or does it belong on the other side of the line? So this is what it looks like. Just mathematically, if you put them, on a board, it might look a bit more like this, which is we would say, okay, I want to take each of my variables, my two input functions, x1, x2, given humidity, given pressure. I want to multiply them against some weight. I don't know what the weight is yet. That's fine, but there's going to be some kind of a number. There's going to be some, maybe like weight 1, weight 2. I don't know what it is yet, but we're just going to multiply against them. And maybe we just want to add some other, something else called a weight 0, because my function might require us to actually, you'll see why later, but it might just able to shift the entire value up or down by a certain amount, okay? And we just compare. And then we just say, okay, we then compare them. So we multiply that by a weight, and then we just compare. We do all the maths, okay? And then we say, is it greater to, or is it equal to 0? Now, okay, so if you now categorize that data point as a rainy day, perhaps, because now we're going to try to put that on a bigger than and smaller than. Otherwise, we might say no rain. Okay, so the key then is that this expression how are we going to calculate if it's a rainy day or not, okay? You know, what we're going to do is a whole bunch of maths and just take each of those variables coming through, each of these variables, so x1, x2, x2, and then we're going to multiply those variables by a weight, okay, some kind of level of importance or gravitas, shall we say, to this, and then maybe just add an extra weight to it, as we're going to see in a second. That's like just another thing. But the point here is that we're trying to see, given those two things, is it greater than or is it smaller than 0? Is it over here or is it over there? You know, the result of which is it greater than or equal to 0. And then using the result of that expression, we're able then to determine whether it's raining, whether it's not raining. So the expression in this case is, again, just referring to some kind of a line, between data points. If you're going to plot this graphically, as we'll see in a second, it would just be a line. What that line looks like depends on those weights, you know, to this. So just again, to be really clear, x1, x2 are the inputs, okay? But the weights, w, that's what determines the shape of the line, okay, or the slope of the line, if you will, what that line really looks like. It's not always going to be straight as an arrow, okay? So if you imagine literally like a line like this, and if I put a little bit more weight on this part here, you know, I kind of lean on this end, it might just it might tip over somewhat. If I put more weight there, it might, you know, tip this way as well too. So the weights are somehow going to bend that line, okay? That's going to be the great classifier, the great divide. They determine the shape of the line. The point here is that we want to figure out then what those weights should be. We don't know yet, okay? We can choose whether, we can pick at random, just pick numbers out of the bag and just say whatever weights do we want there. But we want to choose our weights in such a way that, again, if you pass in rainy day's humidity, rainy day's pressure, you end up with a result that is greater than or equal to 0. Let's imagine that, remember, so blue being greater than or rainy, and such as if we pass into a hypothesis function that a non-rainy day, so red for non-rainy, then that should always be less than 0, okay? The numbers should output in that such a way, okay? I know, but before we try and get there, okay, just try to formalize this a little bit more mathematically, okay? Just because right now that's just to get a sense for how you might often see this if you do further go into this, okay? Supervised machine learning and try to explore this idea. One thing that you generally, for these categories, sometimes you'll just use the names of the expression or the categories like rain or not rain. But, you know, we're just saying this to make this easier. Mathematically, if you're trying to do comparisons between these different things, it's just easier often to deal with the world of numbers. So in that case, we could just say that 1 and 0, okay? So 1 is for, we said 1 is for raining, and 0 for not raining, okay? Just because mathematically that cleans up our thoughts somewhat. So if we do all of this maths, nothing has changed. It's the same as the slide before. We're just going to clean this up, shall we say. So if the result of this is greater than or equal to 0, so 1 or above, okay, we're going to go ahead and say then our hypothesis function outputs 1, meaning it's going to rain. Otherwise, if it doesn't, then it outputs 0, meaning not raining. So oftentimes you'll this kind of expression here, this instead expressed using vector maths. So the vector is, again, if you're not familiar with the term, a vector just refers to a sequence of numbers, of numerical values. You could represent them in Python with like a, just a list, I guess. In Python, you could do that with a dictionary, or just basically a list of numerical values, one after the other, okay, or a tuple with numerical values. And so here what we have is a couple of sequences I'm going to show you now with numerical values. So one of our vectors, one of our sequences of numerical values are all of those individual weights. So W0, W1, W2. And we could try to construct this in such a way that we'll call this a weight vector. We'll see why this is useful in just a moment, okay? Generally, we're going to call this, or abbreviate this as W, generally represented with the bold-faced W. So like this, it's kind of boldened. But this is just going to be a sequence of those 3 weights. Weight 1, weight 2, well, weight 0, weight 1, weight 2. And just to be able to calculate then, based on those weights, whether or not we think a day is going to be raining or not raining, what we want to do is then multiply each of those weights by our input functions from we saw earlier, okay? So here, for example, this second weight is going to be multiplied by input variable x2. So W2 is going to be multiplied, side by side means times by, okay? Going to be multiplied by that input x2. Same goes here, okay? That's going to be multiplied, weight 1 is going to be multiplied by input variable x1. And this weird one here on the side, well, it's not actually being multiplied by anything, okay? But really this is just here so to make sure that the vectors are the same length, okay? Well, I'll show you again why that's useful in just a second, but we'll just go ahead and say that W0 is going to be multiplied by 1 because, you know, you can multiply anything by 1 and you end up with the exact same number, so that's fine. So in addition to the weight vector being up here, what we would like is then to have an input vector. Well, we just call this input vector x again. So we're multiplying weight 0 by 1 and then eventually x1 and then x2. So here too, we've represented 2 distinct vectors, a vector of weights that somehow learn, okay? So the goal of machine learning and this algorithm is just to try to learn what this weight vector is supposed to be. You know, we could try any arbitrary set of numbers. We could just go through one at a time and we could produce a function that tries to predict whether it's raining or not raining. but it probably wouldn't be very good, okay? We can't guess these things. So what we would like them to do is to come up with a good choice of those weights, a realistic set of weights, so that we can try to have we could do the accurate predictions. And then this input vector down there, that represents a particular input to the function, okay? So this particular input data point for which we're going to then, the thing that we would like then to go ahead and estimate for, okay? So is it going to be rainy? Is it not going to be raining? Is it counterfeit? Is it real, okay? And that's just going to vary again, depending on what input weight is provided to that function. You know, what is that we're trying to estimate? And then we try to do the calculation. We want to calculate this expression down here, okay? It turns out then that this expression is something we would generally call the dot product of those two vectors. Okay, so a dot product of two vectors means that we're just taking each of those two terms in the vectors and then multiplying them by each other. So W0 multiplied by 1. X weight 1 divided this times by that. This times by that. Okay, and that's why these vectors need to be the same length. Okay, and we just add the results all together. So this times by this. Sorry, that's really messy. This times by this, that times by this, that times by that. Multiply, you know, times them all together, and you end up with the dot product. I know. I wanted to show you this a little bit theory-wise because then it'll then help to see this more visually. Okay, when I do get open the lab. So the dot product of this W and the X, then, you know, we could call this the weight vector. We could call this the input vector. That's really just going to be weight 0 or just W0. Okay, plus weight 1 times X1 plus W2 times X2. And then, so we then have our weight vector, which is what we need to then figure out. We need our machine learning algorithm to try to figure out what the weights should be. You know, we had the input vector representing the data point, which we're trying to we're trying to predict a category for. We're trying to predict a label for. Is it fake? Is it real? Is it raining? Is it not raining for? And then we're able to do that calculation just by taking, again, that dot product, which you're going to see represented in a like this, like in a vector form. But if you haven't seen those vectors before, you just think of it really as being identical to the mathematical expression. Just doing the multiplication, okay, adding the results together, and then seeing then whether the result is going to be greater than or lesser than or not. Okay, so this, again, this expression down here, so weight 1 times by x1, weight 2 by x2, this is identical to that above here, okay? We're just trying to calculate whether or not that actual answer is greater than or equal to 0. Okay, so for that reason, okay, you'll often see the hypothesis function, h, written as something a bit like this. This is a simple representation of where the hypothesis just takes in as input an input vector input vector x, okay, some humidity, some pressure, some rainy day, whatever it is, those two things. And then we would like to predict an output like, rain or not rain, if we try to represent those things numerically, okay? And the way we do that is by taking the dot product of those weights and our input. So it's greater than or equal to 0, then we're going to go ahead and save that input as 1. Otherwise, the output is going to be 0. And then this hypothesis we've just parameterized the weights by, depending on what the weights are and what we choose, we're going to end up getting a very different hypothesis. So if we choose the weights at random, we're probably not going to get a very good hypothesis function, okay? We're going to get a 1 or a 0. But it's probably not going to be very accurate, you know, to reflect whether we think a day is going to be raining or not raining. But if we choose the weights function, it's got a weird message notification. So we try to do a very good, we sort of estimate whether we think the output of the function should be a 1 or should be a 0. And so the question is then to figure out then how the weights should be, you know, try to tune those parameters. And there are a different bunch of ways that you can try to do this. One of the most common ways around this is called the Perceptron learning rule. Okay, and we'll see a bit more of this later. But the idea of the Perceptron is, and we're not going to get too deep into the maths here, I'll try not to, okay? But just try to introduce the ideas, if you will, more conceptually, is to say that given some kind of data point we would like to learn from, some kind of data point that has an input X and an output Y, where Y is 1 for rain and 0 for not rain, then we would try to then update the weights. And we'll look at the formula in just a second, okay? But the bigger picture here is that we start with random weights and then learn from the data. Like, you know, take the data points one at a time. And for each of the data points, figure out, okay, well, what parameters do we need to change inside the weights in order to then better match the input point? And so that is the value of having access to a lot of different data, a lot of access to, well, the supervised, in supervised machine learning, you know, taking each of the data points and maybe looking at them multiple times over and then constantly trying to figure out whether you need to shift your weight according to create a better weights vector that is going to be able to more correctly, more accurately try to estimate what the output should be, okay, whether we think it's going to be raining or not raining. So what does that look like? Like this, okay, without going too much into the maths anymore, we're trying to update each of the weights to try to be the result of the original weight plus some additional expression, okay? And just to extend what the expression Y is, well, Y is what the actual output is, okay? And the hypothesis of X, the input, you know, that's going to be what we thought the input was. So I can replace this by saying, you know, what the actual value was minus the estimate was. So this is based on the difference, the delta between the actual value and what our estimate was. So how far off were we? You know, how wrong really were we? we might then want to change our hypothesis based on this. Okay, we want to change the way we do our estimation, because if the actual value and the estimate were the same thing, bang on, okay, bullseye, meaning we were correctly able to predict what category that data point belonged to. We got it the first time round. Well, then the actual value minus the estimate, how far off really were we? That's just going to be 0, which means this whole term on the right-hand side goes to be 0. Then the weight doesn't change. So weight I, where weight 1 or weight 2 or weight 0, weight I just stays weight I. Okay, none of the weights really change if I was able to correctly predict what category the input belonged to. But if our hypothesis doesn't correctly predict what category the input belonged to, then we need to make some changes. Okay, we need to then adjust the weight in order then so that we're better able to make or predict this kind of data point in the future. What is it the way that we want to do this? Well, again, so if the actual value was bigger than the estimate, and for now, let's just go assume that these are positive integers, they're just above. Okay, if the actual value is bigger than the estimated value, then that means we need to then increase the weight in order to account for that. Okay, in order to make the output bigger, and therefore we're able to get more of the actual value. And so the actual value is bigger than the estimate. Okay, the actual value minus the estimate means that'll be a positive number. So you can imagine that we're just trying to add some positive number just to the weights, just to increase it ever so slightly. And likewise, the inverse is also the true. Okay, the actual value was less than the estimate, so the actual value was 0, but we estimated 1, meaning it was not raining, but we predicted it was going to rain. Then we want to decrease the weights, because then in that case we want to then try to lower the total value by computing that dot product, okay, in order to make it less likely that we would predict something that we would be raining or not. But there's no need to go into too much of the maths for this, okay? The general idea is that every time we try to encounter some kind of data point, we can adjust those weights accordingly and then try to make our weights better line up with the actual data that we have access to. So we can sort of rinse and repeat this process with that data point, and then eventually, hopefully, your algorithm converges, to some set of weights that do a pretty good job of figuring out whether a day is going to be raining or not. And that's this, okay? Just as a final point about this particular equation, okay, this value here, alpha, that's something that we're going to call the learning rate. So again, just some parameter, just a number we choose here, just how quickly we're actually going to be updating those weight values. So that if alpha is bigger, then we're going to be updating those values a lot faster. And again, if it's smaller, then we're going to update it by a lot smaller. So you can choose the values of alpha depending on the problem, okay? Just different values might suit the situation better or worse than others for that. So then after all of this then, after we've done all the training process, after we've taken all the data in, after we're using the learning rule, looking at all the pieces of data then, using each piece of data as an indication to us as to do the weights stay the same? Do we increase the weights? Do we decrease the weights? And if so, by how much? What we end up with ultimately is a threshold function. What we end up with and what we try to find then is that line, okay? And so when we can look at that threshold function, that looks a bit like this in that case. So again, on the x-axis here, we have the output of the function. So we're taking the weights and the dot product together here with the input. And on the y-axis, we have the output is either going to be a 1 or a 0. Okay, so in this case represented as, is it not raining? 1, and 0, it is raining. So okay, it's just representing different states. And the way that the hypothesis function works is by calculating then the value. So is it greater than 0? Okay, or is it greater than or smaller than some threshold? Then we declare it to be rainy day. Otherwise, it's not going to be a rainy day. So graphically, this is what it more or less looks like. Okay, so here is that value. And then this is, at least initially, the value of the dot product is small, raining, not raining, not raining. But as soon as that anything crosses a function, as we enter then into 1, we suddenly say, okay, well, now it's definitely raining. Now it's absolutely definitely raining. So the way to sort of interpret this representation is that anything on this side of the line, okay, that will be the category of the point that we say, yeah, it is absolutely raining. Anything on this side of the line is where we say, the data point where we say it's not raining. So again, we want to choose some value for the weights of the result in the function that does a pretty good job at figuring out this estimation for us. The one tricky thing or that kind of hard thing to do is get this threshold right when we have, right now we're only seeing 2 possible outcomes, 1 and 0, okay? So we plug some data as input and the output is going to get raining or not raining. There's no room for in between, if you know what I mean. There's no half in, half out. And maybe that's what you want, maybe that's fine. Maybe that's what you want is like given some data point, you would like it to be able to classify into like 1 or 2 or more of those different categories. But maybe we also want the case then that just, like we want to know just how strong the prediction is. So for example, if I go back to this one here, we're going to have rainy days on one side of the line, blue, and then not raining on red on that side of the line, then you might imagine this then somehow then try to predicting these white data points there. So this data point here we would like to do is predict a label for this data point here, and then we would also like to predict a label for that one. Seems pretty likely that one should be more of a rainy day than the other one. So it seems that one of these is much more strongly rainy because they're both rainy. They both fall on this side of the threshold line. But clearly, I would say, which again, with more confidence, shall we say, that this particular data point is more firmly footed. One, because, yeah, it seems a lot closer to the, if we go by the nearest neighbor hypothesis from earlier on that strategy, if it's on this side of the line, again, if we're just going by the strategy saying, like, what's close by, does it fall on figuring out what those weights should be? And if we're using, again, the line category of just saying which side does it fall on, well, we would also say that, yeah, it is a rainy day because it falls on the side of the line here on the right-hand side, which corresponds to rainy days. But it's likely then that even in this case, we would, we would know that it doesn't quite need to fill me with confidence nearly as much because, say, this one compared to that one, yeah? So for this one on the right, I would feel very confident that, yeah, it is super rainy. This one on the left is pretty close to the line if you're judging it again by just by distance. So I'm less sure about that one. Let's just wrap up the point and we'll go for a little bit of, I will go for a coffee break. But just to see this in action, if the threshold function doesn't allow for a notion of like sureness, if you're saying, yeah, like we don't really have a way of saying this. I can't really say I'm not really sure, I'm more sure about this one than that one, then that's something that we would call a hard threshold. Because once you've crossed this line, then immediately, it's going to be a rainy day. Okay. Anywhere before it, it's going to be a not rainy day. And that's helpful in some cases, but one, this is not a particularly easy function to deal with. And if you get deeper into the world of machine learning and trying to do other things like taking derivatives of these curves, this type of function makes things really, really challenging. But the challenge is that we don't really have any notion of gradation between things. Yeah, we don't really have a notion of, it's a really strong belief, but that it's going to be raining as opposed to it is probably more likely to be than it's not going to be raining, as was mentioned earlier. So, but we're not totally sure about that either. So what we can do is by taking advantage of another technique known as logistic regression here. So we're trying to look into something that looks a little bit more curved like this. So something that more curves nicely, okay? And the result here is that we have the possible output values that are no longer just 1 or 0 like before, so 0 for not raining, 1 for raining, but you can actually get any number of real values between 1 and 0. Yeah, so this side on the left-hand side means that if you get a value of 0, again, it's not going to be raining, we're pretty sure about this, and if you get it on that side of the things, you do get a value of 1, we're very sure that you're going to be raining. But in between that, okay, you could get some real numbered value, a value like 0.7, 0.9, where we think it's going to rain with high probability. It's more probable that it's going to rain versus, based on that data, but we're not as confident as some of that, some of the data points might be instead. So again, one of the advantages of the soft threshold here is that it allows us to have, again, some output that could be a real number, some decimal point that potentially refers to any form of probability. The likelihood that we think of this particular data point here is belonging to a particular category, and so some nice properties thereof too. Okay, I think we can maybe get as far as the Markov decision tree. I would ideally like to show you some of this stuff in action. So if we just rewind a moment or two, what's function regression? I think regression would be a good one to start with. Because what I'm trying to do is just expose you to a lot of these algorithms out there, at least the most popular approaches of which. So if we have a set of data and we would like to learn something of it, okay, we have something that's better known as a support vector machine. And again, just to explain this more visually what it's going to be like, the idea or the motivation, shall I say rather, behind the support vector machine is that there are actually a lot of different lines that we could draw on this stuff, okay? A lot of different decision boundaries that we could do in order to separate these two groups. I could put this over there, over here, over there. So for example, if I had from before the same red data points here and the blue data points there, one line I could draw is something a bit like this. Okay, so this line would separate the red points from the blue points. And it does it perfectly, it works. All the red points are neatly onto one side and then the blue points are also on the other side of the line, but it should probably make you feel a little bit nervous, okay? Because if you come up with a model and that model comes up with a line that looks like this, and the reason why you want to worry about this is that it's going to try to generalize to other data points that are not necessarily in the same data point that you and I might have access to, okay? So, imagine like you might have a red point somewhere over here. Very reasonably then, you would just say, if something fell over on that side of the line, okay, on this side of the blue of this line, then based on this, we might want to guess that, yeah, it is in fact a red point, but it falls on the side of the line where instead we would estimate then it's actually blue because it falls on that side of the line. And so based on this, then it's probably not the great choice then because it's just so close to what those various data points are. And so what we might prefer then is not this particular line, but then reach towards something more diagonal, okay? Something that just diagonally goes across the data like we've seen already before, okay? But then too, there's a lot of different diagonal lines that I could draw, okay? We could draw that as well in many different forms. It starts to get a bit tricky. So for example, I could draw this diagonal line up over here, which also again successfully separates all the red points from the blue points from the perspective of just trying to figure out whether, or some setting of the weights that allows us to predict on the correct output, this white line here will correctly predict the output for this particular data set every single time. Because again, the red points are on this side of the line and the blue points on the other. But again, I feel really nervous looking at this because this line is just so close again to those red points, which even though, yes, we are able to correctly predict on the input data, there was a point that sort of kind of fell in the middle here. Somewhere in this area, this kind of general algorithm, this model then would say, no, we think it's a blue point, but actually in reality, it might more appropriately belong to on the red category instead, just because it looks like it's closer to the red points. What we really want to be able to say then is, given this data, okay, how can you then generalize this out as best as possible? Now, it would be somehow to come up with a line that looks more or less like this. Then it seems like the more intuitive thing to do, just to draw this down the middle. And the reason it's intuitive is because it seems to be kind of as far as possible from the red side as well as the blue side too. We've got some space between us. So that if we generalize a little bit and we start to get our elbows out and we assume that we have some data points that are, again, different from the input but slightly still further away, then we can still say that, yeah, something on this side of the line probably red, something on this side probably blue, and we can make those judgments either way. And so that is what this support vector machine is designed to do. Vector machines, on the other hand, well, they're designed to try to figure out what we call the maximum margin separator. Okay, the maximum margin separator is just some boundary that maximizes the distance between the groups of points. So rather than us coming up with just one boundary that's, again, very, very close to one side or the other, where in like the case before we saw, we just wouldn't have cared, as long as we're categorizing the input, well, that seems all we need to do. Okay, the support vector machine will just try to find this maximum margin separator, some way of then trying to figure out or trying to maximize that particular distance. So it does this then by figuring out what we call the support vectors between the vectors which are, again, closest to the line, just to try to maximize the difference between the line and the particular points. The way that it works is in 2 dimensions. It works in high dimensions too, where we're not looking for some line that separates the data points, but instead looking for what we generally call a hyperplane, okay, some decision boundary again. Effectively, something that's going to separate one set of data from the other set of data. And this ability then of support vector machines to work in high dimensions actually has a number of other applications too. But one that's really helpful just to deal with is where data isn't that linearly separable. So we talked about the linear separability before. Just this idea that you take some data, you just draw a line then, or some linear combination then of those inputs, just allows us to be more perfectly separate 2 sets from one another. There are then some data sets that aren't as linearly separable, where again, in even 2, like you wouldn't be able to find a good line at all, given that we would try to find some kind of separation. So something like this, for example, where you can imagine here, okay, so here are the red points and the blue points around this. I'm asking you, try to find a line. Try to find a line that somehow divides the red points from the blue points. It's going to be really hard, if not impossible to do so, because any line that you choose, really, if you draw a line here, you kind of all ignored all the blue points that you actually should be blue and not red, or kind of any way you draw the line, there's going to be a lot of error, okay? A lot of mistakes, a lot of what we call loss to that line that we draw. A lot of loss is what we call the data points that you're going to categorize incorrectly, okay? So what we really want to do is to try to find a better decision boundary, okay? That might not be a straight line anymore through this 2-dimensional space. And support vector machines, well, if we start to imagine, Mohammed, exactly right, we start to operate in high dimensions and try to find some other decision boundary, like a circle. The circle in this case, that's actually going to be able to separate one of those sets of data from the other ones a lot better. So oftentimes, like in data sets where the data is not as linearly separable, support vector machines, by working in high dimensions, you can then try to figure out actually a way to solve that problem more effectively. So that then, these 3 different approaches we've seen. Well, we've seen support vector machines. We've seen trying to use linear regression as a line, and the perceptron learning rule, again, just to try to figure out how to categorize the inputs and the outputs too. We've also seen the nearest neighbor approach. But again, not one is necessarily better than the other one, because it's going to depend on the data set. It's going to depend on the information that you have access to, and it's going to depend, again, on the function itself, the thing that you're ultimately trying to predict. And so this is where a lot of research, a lot of experimentation can be involved in trying to figure out how is it best to perform that kind of estimation. Classification is just one of the tasks that you might find in supervised machine learning, because in classification, like, what we're doing is we're trying to put a label on things. We're trying to predict some discrete category. We're trying to predict blue or red, rain, not rain, real, not real. Okay. Sometimes what we want to do though is predict a real numerical value. So rather than it being classification problems anymore, we have a related problem, not classification anymore, but instead known as regression. Now, regression is the supervised learning problem. So if I say classification versus now regression, again, so classification assigns input data to predefined categories. What if we now want like a function mapping input to outputs, but same as before, instead of the outputs being now discrete categories, rain, not rain, like in what we want now is to get some output values which are generally continuous. Okay, some continuous values like numbers we would like to try to predict. And this happens all the time as well. Okay, you might imagine like take a company or like this approach if you're trying to figure out the housing price prediction, what's the effect of something, what's the effect of advertising. You know, how much does advertising spent translates to the stock price of a company's product? Something like this. So they might then try to predict some function that takes as input the amount of money that's spent on, say, advertising, okay? And here what we're going to see is just use one input just to keep things nice and tidy. But again, you could scale this up to many, many more inputs as well if you have a lot of different kinds of data you might have access to. The goal here is just to try to learn a function. Machine learning is trying to say, given this amount on spending, like spending on advertising, how much money we put on billboards and such, well, we're going to get that much out in sales. So you might judge this on having, you know, based on having a whole bunch of data, like for every past month, how much we spent based on advertising, here's what sales were. We would then like to try to predict some kind of a hypothesis function that, again, given the amount of advertising, we can predict in that case some real number out of this, okay, some estimate as to how much sales we would expect that company to be able to yield in this month in order quarter unit of time as well too. Yeah, even in an area. So as an example, if I put this into this, so this, again, this approach of solving the problem, we try to use a linear regression approach. Linear regression, again, think of a line where we take this data and we just kind of plot this out there. On the x-axis here, we had advertising dollars, like money basically thrown at the problem. On the y-axis, we have sales. So we might try to draw a line then that just does a pretty good job at kind of estimating or guesstimating a relationship between advertising and sales, so that we want to figure out then what the estimate is. Okay, if I put this much money in, that much money will come out, okay, for a particular budget. Or we just look at this line here and then just try to figure out then this amount for advertising, we would have this much for sales and make the estimate either way. So if you can try to come up with a line then, again, figuring out how to modify the weights, again, different various techniques to try to make it so that this line fits as well as possible. Well, yeah, what we're trying to achieve then is solve machine learning styles and problems. The question becomes then, how do we evaluate them? Yeah, like how do we evaluate the various types of hypotheses that we could come up with? Because we've just seen a couple of algorithms and they more or less give us some kind of hypothesis, some function that maps inputs to outputs. Well, how do I know if they're any good or not? They could be terrible. How do I know if that function works? And so you could try to think of these hypotheses as trying to get a better, you know, working and trying to get a better hypothesis as kind of like an optimization problem. So in an optimization problem, you can, like you're trying to maximize some objective function, like a minimax, trying to find a global maximum. Are you trying to minimize a cost function? Okay, trying to get more good behavior, reduce bad behavior, trying to figure out some around this. And in the case of evaluating these hypotheses now, you know, one thing we might say is that this cost function, the thing we're trying to minimize, okay, the bad behavior, we might call that instead a loss function. And so what a loss function is, it's a function that's going to expresses how poorly our hypothesis performs. So more formally, it's like a loss of utility. So whenever we predict something that's wrong, that's a loss of utility. Gosh, I can't type. So that's going to add to the output of our loss function. And so you can come up with any loss function that you want, you know, just some mathematical way of estimating, given these data points, given what the actual output is, and then given what the projected output is, our estimate, you could sort of calculate what numerical loss forms from there. Just to visualize this a bit better, okay? Because in this case, if I go back to my classifying days as rainy as not rainy, how much better is it drawing, you know, the line here or drawing the line there? Because we could take each of the input data points has a label, whether it's raining or not raining, and we could compare it to the prediction, okay? Because we predicted something about raining or not raining, and then assign it some numerical value as a result. In the notion of evaluating then, for example, these data points over here on the right-hand side, they were all rainy days in blue. And we predicted they would be raining because they've all in the bottom side of the line. So they had a loss function of 0, you know, nothing lost from those situations here. Likewise, same is true for these data points up top where it wasn't raining and we predicted it wouldn't be raining either. But where we do have some loss is, like the data points here, for instance, that one there, obviously, my pen's not working because it's in black, but now there and here and also there too. So like basically the contrapoint, okay? So it was a red point in actuality, but we predicted otherwise when it wasn't raining. And so as a result, we miscategorized these data points when we were trying to train on, okay? As a result then, there is some loss. There is some loss function here, okay? There's one loss here, one loss there, and here and there too. So there's a total of 4 loss, okay? So there's no real better way than these 4 points of loss if you're just drawing a straight line through our space here, because anywhere else is going to have some figure of loss too, okay? So the 0, 1 loss function says, like, did we get it right? Did it get it wrong? Did I get it right here? If we get it wrong, then our loss function for that data point says 1, and we add up all those losses across all our data points to get some kind of empirical loss. You know, how much did we lose across all the original data points we had that our algorithm had access to? If I can just jump a little bit forward in the story, because I don't want to get lost in the loss function so much stuff, so that we can get into more of the Markov model. Okay. I mean, there are trade-offs that I think we can leave for another night, because regardless of the loss function, like how far off were we, there's always this fundamental risk in machine learning models that we call overfitting. Now, overfitting is when a model fits too closely to a particular data set and therefore may fail to generalize future data. Okay, so we want our model to be able to learn patterns from data, but not memorize specific examples. Why? Because the real goal of machine learning is just to have this in mind and then apply what you've learned to then new data, unseen data, things in the future that hasn't been trained on, rather than just repeating what it just saw in training. So think of it this way: like, say you're training a model to distinguish. I'll show you in a second, like real things from fake things. So overfitting in machine learning. If I'm going to train a model to differentiate between real banknotes or counterfeit banknotes, if the model memorizes the exact characteristics of those bills, like of the training data set, then it might get 100% accuracy on those bills, but it would completely fail when it's faced with new counterfeit that has slightly different patterns. Okay, that's overfitting in this case. It's when it performs too well on the training data, but it fails to adapt to new examples, to new problems. So we can visualize this problem a bit more. Like again, rainy day classification again. If we put all the data points for rainy day, not rainy day, a good model here would draw a simple line that separates again these two groups, allowing some mistakes, but still capturing the general pattern of the data. But the empirical loss isn't zero in this particular case because we didn't categorize anything perfectly. Yeah, there was one red outlier here. You can see on this one day that it wasn't actually raining when it turned out to be. Okay, but the model still predicts that it's going to be raining. Doesn't necessarily mean that the model is bad or broken. It just means that the model isn't 100% accurate. However, like if you really wanted to try to find a hypothesis that resulted in minimizing the loss, okay, you could come up with another decision boundary, which wouldn't be a line anymore. It would be one of these jaggedy kind of crazy enclaves that look somewhat like this, okay? So the decision boundary does what it has to do. It still separates the red points from all the blue points because the red points fall on this side of the line, on this side of the decision boundary. The blue points fall on that side of the decision boundary. But again, we would probably argue, not be a very good prediction because, like, yes, it is more accurate, quote unquote, based on all the available training data we might have for the training on this machine learning model. We would say that this is probably going to generalize really well. It's 100% accurate. That if there were other data points like this here and there, we might still want to consider things around here, rainy days, because we think that's probably an outlier. But an overfitted model would then attempt to perfectly classify every single data point. And what you end up with is like jaggedy, complicated boundaries and bends and twists that do correctly classify every training example. And that does mean that we would fit to some random noise. And this is a problem. This is a real issue because that complicated decision boundaries might not work very well on all the new unseen data in the future. So if the thing that you really care about is minimizing the loss on the data that you have available to you, you run the risk of overfitting. And this can happen when you misclassify something. The same thing happens with regression too. So let's say if I'm trying to predict sales based on advertising like before. Okay, so what we predicted we thought was a pretty good line, again relating to sales, this time regression, so continuous numerical values, trying to predict what sales are going to be for any given amount of spend on advertising, something along those two matrices. I could come up with a line that does a better job of predicting the training data, okay? And that would be something like this. And just connecting all the different various data points. And again, there is no loss at all. I've perfectly predicted any advertising what sales would be, and for all the data, all the available data to me, it's going to be 100% accurate. A reasonable model would try to find a general trend between advertising and sales, maybe like drawing a somewhat smoother line through the data. But what we see here is an overfitted model where you create this complicated zigzag through every data point, and it captures all the randomness, all the noise, all the fluctuations, rather than a true relationship. Okay, so this is overfitting. Overfitting is not going to generalize very well. If I am overfitting training data that's available to me, we obviously want to avoid this. We would like strategies to make sure that we have fit our model to a particular data set as well as possible. And there are a few ways around this. There are a few ways that we can prevent overfitting. Because if we want to avoid overfitting, we then want strategies to make sure our model generalizes quite well to new data, things in the future. Okay, so one way that we can optimize this for, okay, in an optimization problem is so all we say is that there is some cost, okay, and I want to then maximize that cost. And so far we've defined that cost function, again, the cost of the hypothesis just being equal to the empirical loss of that hypothesis. So how far away from the actual data points, from the actual outputs away from what I predicted them to be based on the hypothesis. So if all you're trying to do is minimize loss, meaning you're minimizing the loss in the case, the result is going to be that you might overfit. So that to minimize cost, you really try to find a way that perfectly matches all the input data. and what might happen as a result of overfitting on that particular input case. Like, in order to address this, you could try to add something to the cost function, not just loss anymore, but also some measure of complexity of the hypothesis, where the complexity here is just something you would then need to do to define how complicated does a line look. This is sort of an Occam's razor thing. So we want to give preference to a simpler decision boundary, like a straight line or a smooth line. Okay, there's some like a simpler curve as opposed to a much more jaggedy, kind of crazy looking line, something that's going to represent the training data better. Okay, it might not generalize as well. We will generally say a simpler solution is probably the better solution, and probably the one that's more likely to generalize well to other inputs as well, unseen inputs. So we measure what the losses are, but we also measure the complexity. Okay, and now all that gets taken into account when we consider the overall cost. That, yes, something that has less loss and predicts better than the training data, but if it's way, way more complex, it might not be the best decision we saw. Okay, all we need to do is come up with a bit of balance between loss and complexity. And that's the parameter lambda in this case. Okay, and we're saying like lambda has a greater value. We really want to penalize more complexity. It's like if lambda was smaller, we're going to try to penalize more complex hypotheses a little bit too. And it's up to the machine learning kind of programmer to decide whether they want to set that value of lambda to how much do I want to penalize for a more complex hypothesis that might fit the data a little bit better. And again, there's no one way of doing these things. A lot of things depend on the data set, depending on the data you have available to you, the problem that you're trying to solve, the choice of parameters. You might need to experiment a little bit too. Okay, and we'll see. Now, regularization is that process of penalizing the hypothesis. So I'll get to SageMaker in a bit. Okay, so is the process we're trying to make it a bit more complex, basically. And so in order to favor a more simple hypothesis that's meant to generalize better, okay, I'm more likely to be able to apply this to other situations that are dealing with more input points or ones that we've necessarily seen before. Quite like Amazon's page. I'm just going to go for them. So oftentimes you'll often see this as regularizing, as to a term that we're trying to minimize it in order to avoid this problem of overfitting. So it's the process of penalizing complexity. Like the idea is if you give the model too much freedom, it might start to memorize the data rather than learning useful patterns. So in order to prevent this, you might add you might regularize it. Okay, you might add that to the loss function, which again discourages overly complex models. This is a little bit too out there today, I think. If I can just get to... Okay, so let me just explain what I'm going to do, because just before I do, let me apply one way of doing this. So if what I would like to do is to regularize my data, one way... Okay, so let me explain this just very quickly. If I'm trying to prevent overfitting with folding, so I don't want to run the risk of overfitting on my experiments, on my model, okay? Because I'm training a model, okay? Whether or not we were able to generalize that model or create onto other sets as well, it's for the reason that often, like when you're doing machine learning assignments and experiments, you've got some data and you want to be able to come up with some function that predicts some input, okay, what the output's going to be. But you don't necessarily want to do your training on all the data that you have available in one go, okay? So you might employ something that's better known as a holdout. So with a holdout, what you do is you split your data. Okay, you split your data into a training set and a testing set. So you basically put them into two parts. So holdout is, well, one method of splitting your data into a training set and a testing set. And the training set here is going to be all the data that we're going to use to train the machine learning model, whereas the test set is going to be the set of data that we're going to use in order to test and see how well the machine learning model actually performs. Okay, so the learning happens here. The learning happens on the training set. We figure out what parameters should be. We figure out what the right model is. And then we see, okay, now that we've trained the model on this data there, let's see how well it then performs at predicting things inside the testing set. The same set of data that we just haven't seen before, the other side of it too. The hope then is that we're going to be able to predict the testing set pretty well, is we're going to be able to generalize based on the training data that's available to us here, if we've actually overfitted the training data. Though, and we're not able to generalize, if we're able to look at the training, if we're able to look at the testing sets, it's likely then that, well, it's going to be the case that it's not going to be able to predict things that aren't in the training set as well. Okay, so what we're trying to figure out is, have we overfitted? If we've overfitted on the training sets, we're not able to generalize then. We're not able to look at the test set and see those same patterns. Okay, it's going to be likely then that the model it's not very effective. Okay, it's not learning things as well. So this is one method of cross-validation, okay? We're validating to make sure the work that we have done is going to be able to generalize to other data as well. Okay, and there are other statistical techniques we can see too. One that's known as k-fold validation, which just means rather than divide things into just two sets an experiment, we divide things into k sets, like k different amount of sets, maybe say 10 different sets, and then we run 10 different experiments. So instead of dividing into just 2 and 2 and running like one experiment, we divide this into all these different k subsets and then run k different experiments. It's like turning the clock around 1 hour at a time, shall we say. So for each of my 10 experiments, I could hold out one of those sets as the testing set, and then I would, train the model using the other 9. Anyway, so the result is we just end up with 10 different answers for how the model actually worked, okay? And then often you might just take the average of those 10 and then approximately how well it performs overall. But the key idea is that we're just trying to separate the training data from the test data, because you want to be able to test your model on data that's different from yours that you've trained on. Because again, the training, you want to avoid overfitting. You want to be able to generalize your model. You want it to be applicable to the future. And the way you test whether you've actually been able to generalize or not is by looking at some data that it's not been trained on before, that you haven't seen before, and seeing how well it's able to perform, okay, how good it was. And so if I want to, a lot of these techniques inside of a programming language, like machine learning, is often done in SageMaker. Now in Amazon, you'll see like Python is the language of choice often with this, but there's a whole bunch of ways we could do this. We could write this from scratch. There are libraries out there that allow us to take advantage of such a thing, that we can use the same types of algorithms in a lot of different scenarios. Sckkit-learn is one such thing, a very, very popular Python library, which is going to be able to set this up with a lot of different machine learning models. So in this particular model, so there's already written there we go, regression, classification, clustering. This is all machine learning stuff, okay? Things that for doing perceptron learning, for nearest neighbor classification, for doing a bunch of other types of inference and supervised learning that we haven't even talked of yet, okay? But again, just so we can actually test these models and how they perform, I want to look at one kind of approach as we do this more better. So, okay. I know, just let me introduce. I'm going to pull up one thing on my computer just to make this a bit more clearer. All right, so I'm on my computer. I was just trying this a bit before. I'm going to pull up a particular file, which on my left-hand side seems to be very, very long. It's a whole bunch of data provided by Kaggle, which is like a data set provider, basically just information, okay, data. And this banknotes.csv has information about different types of banknotes. So like a £5 note, £10 note, a 50, £20 notes. So people took pictures of different kind of banknotes in the UK and then measured them across different properties of those banknotes, because in particular, how can you tell fake from real UK banknotes? So some human has been able to categorize those banknotes as either being counterfeit or non-counterfeit. And what I've got then is a data set that has this information, okay? So, okay, that's like a tip on how to check it yourself on the Bank of England, but I'm just saving myself the effort and saying I went to Kaggle and I pulled up a data set on fake banknotes, okay? So that's where I got it from, just in case you wanted to know. Yeah, so anyway, we'll take this. Now, what you're looking at here is a whole bunch of rows, hundreds of rows, okay? And each row then represents one banknote. So in total, I have a good, how many banknotes? I have 1,373 banknotes. So this is formatted as a CSV spreadsheet, okay, where just a comma separated value, CSV, represents each of these different fields, if you see what I mean, okay? So we see 4 different input values. So each of these different data points, just information, some measurements that was made on the banknote, and what those measurements were isn't actually that important right now. Skewness, couture, and entropy, whatever, okay? But those measurements aren't as important as the fact that we have access to the data, okay? Just more importantly is that we have data points to a label. Sure. The label on the right-hand side is this in pinkish color, which we see representing either, I can't remember, I think it was 1 or a 0, represents which one? Was it this one? I don't remember which one represents which one. Well, it doesn't matter. We'll figure it out. But essentially, 1 represents fake, or 0 represents non-fake, authentic. Okay. And so according to the labeled data, again, because this is supervised classification, there is a human researcher or people who have painstakingly labeled 1,000 different banknotes on this particular data. Okay, they've said that's real, that's not real, not real, not real, not real, 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 not real. So we have a whole bunch of data here representing a whole bunch of different data points, each of which has slightly different measurements as to what made on that particular bill, and each of which has a particular output value, 0, 0, or 1. So I'm going to say 0. 0 represents it was a genuine real bill, okay? And I'm going to say 1 is a phony, is a counterfeit banknote. And what we would like it then to do is, again, using supervised learning, again, supervised machine learning, where we're trying to supervised machine learning. So this is the type of machine learning where algorithms learn from labeled data, meaning data with both inputs and corresponding outputs. We know this in order to correctly predict or classify nuancing data, okay? We want our model then to take these 4 inputs coming through and then predict what the output would be. We want to train a model that find some kind of a pattern. Okay, that's being able to predict those measurements or something that you could just measure just by taking a photo of a banknote and whether that's going to be authentic or not. So for that, then I do have another file here. How can we do this with a? Well, I'm just going to open up this file. Okay, so this is called banknotes .py. Sure. So it's a Python file, and what it does right now is not that interesting, but I'll just point out a couple of important bits. Okay, so for example, here, if you're inclined to know this stuff, this is importing first of all from, again, so Sckkit-learn, Sklearn, that's what they call it. But more importantly, down here is you've got the model itself being used. So I'm going to use the Perceptron model. Okay, so I'm going to set my model as in it. So I want to set this model here initially as this one. Okay, I'm going to comment out this one just for the time being. I'm going to use the Perceptron model, okay, which is one of those models we talked about earlier. And what we want to do then is to figure out just setting out some kind of weights down below as to be able to divide our data into two different groups. So then with this open, with this banknote.csv open, so that refers to this one, I'm going to go ahead and then read the data from banknotes.csv. And then basically that for every single row in that banknotes.csv file from earlier, I'm going to be able to separate that row into 4 different values, which is going to be the evidence for that row. Okay. The label of which, well, so the label is going to be that final column we saw on the right-hand side, which in the case of 0 is going to be real. Otherwise, it's going to be fake. So effectively, I'm reading data from here from the CSV file. I'm going to divide it into a whole bunch of different rows, like where each row has some evidence, should we say? And those 4 input values are going to be either my inputs to my hypothesis function, and then the label, the output, what I want out of this, is that it's either going to be genuine, authentic, real, or counterfeit, fake. Okay, so that's the thing I'm trying to predict there too. Exactly. So 0 is white. I'm not sure where we got white from, but whatever arbitrary thing I could call it fish. I could call it chips if I really wanted to, but I'm not going to, okay? The final thing I wanted to do then is to separate the data into... Okay, so that's the bit about the how I can split my data into training and then testing. So, you know, some of my data would like to train my machine learning model so we can actually evaluate the hypothesis to see if the machine learning model actually overfitted or not. So we would like to put some aside, and then I would like to hold some out to the other side just to test that model with, okay? Just to see how well it performed. So what I'd like to do is just go ahead and just take, just say, you know, figure out the length of the data and then just take half of it. Just say, I'm going to go and take half of the data, so times by 0.5, and then save that number in something called holdouts. So that's how many items I'm going to hold out for my data just for the testing phase. I'm going to randomly shuffle that up, so it's going to be in a random order. And then I'm going to say, yeah, for the testing, that's going to be all the data up to the holdouts. Yeah, so it's going to be all the data that... So that's going to be, I'm going to hold up that many items, and then that's going to be my testing set. My training set, on the other hand, is going to be everything else. Yeah, so the information that's going to train my model upon. And then I'll say, like, I need to divide my training into 2 different sets. So I need to divide it into my X values, which, so X represents the inputs. The X values I'm going to train on are basically every row of my training data. So I'm going to get the evidence for that row, okay, those 4 values we saw before. And it's basically just a vector of 4 numbers where that's going to be all the input. And then the Y values... Well, that's what are the outputs then I want to learn from? You know, the labels that belong to each of those various input data points. Well, that's going to be the same thing for each row in the training data, but this time I take that row and get what it's labeled as, whether it's authentic and whether it's genuine or counterfeit. Okay, so I end up with with one list of all the vectors of my input data, and one list which follows my same order, but all the labels that correspond to each of those vectors. So then to train my model, okay, finally. Which in this case is just going to be we said we're going to choose the Perceptron model here. So we're going to go for that type. So I'm going to call this function of model.fit, pass in the training data and what the labels for the training data are. And then Sckkit-learn will then take care of fitting the model. You know, it will do the whole algorithm for me essentially. And then when I'm done, finally, I can test and see how well it performed. So I can now say, well, you know, let me go and get all the input vectors from what I want to test on. So for each row in my testing data set, go ahead and get the evidence. And then the Y values, go and get all the testing. So see what the actual label is, if that makes sense. So I want to generate some predictions, and then I'm going to get the model. I'm going to try to predict, based on the testing vectors, predict what the output was compared to the actual data. So the goal is now just to compare testing with predictions, just to see how well we fared. I want to see how well my predictions based on the model actually reflected what the Y values are, because what they were actually correctly labeled as. Because I now have all this label data, I want to assess how the algorithm really did. And this is how we do it. So this is how we compute how well we did. So this zip function here basically just lets me look through 2 different lists. Okay, so one at a time. for the actual value, and then for each of the predicted value. If the actual value is the same thing as what I predicted, then I'm going to go ahead and increment the counter by 1. Otherwise, I'll push it down. Okay, I'm going to increment my number by -1. So at the end, then, is what I can do is I can print out what's the results. Here's how many I got right, how many I got wrong, and then what's my overall accuracy, for example, right there. Okay. All right. So if I were to go ahead and run this thing, if I pull this up for a sec, and then I say Python off banknotes.py. All right then. So that's now going to train on the data set and, well, on half the data, should I say? Yeah. So the result again for my Perceptron model in this case, I was able to classify 642 correctly as either authentic, as real bills, and then I then incorrectly classified 44 of them for an overall accuracy of 93%. Okay, so on this particular data set, using this particular Perceptron model, we're able to predict pretty well with 93% accuracy what that was going to be. And again, we can try it. I'm just going to try that again, see if I get different results this time. 95 this time. 97 this time. Okay, this is why training data comes through. But before I keep pushing that boat forward, I'm going to try with another model as well. Because what I said, this Sckkit-learn library makes it quite simple for us to just swap out other ones for another training data too. So I'm going to try now. So instead of the Perceptron model, I'm going to use the support vector machine, SVM, which we saw earlier. So, using something inside of which called the support vector classifier. So using support vector machine just to classify things into 2 different groups. So I'm going to save that up. And then this time, if we run the same thing again, let's see how this performs. Now, okay. So this time, much better able to predict then correctly, 99.71. So incorrectly predicted 2 out of 600 and half the data set. Yeah. So we could try another one. Let's try the k nearest classifier. So remember before we saw where k, we take a parameter of k and we see like how many neighbors we want to look at, or n being the neighbors you want to look at, n for neighbors. Let me try this one out. So I'm going to uncomment this one out. So we're going to now use the k nearest classifier again. So this is all part of the Sckkit-learn library, in which you're going to find Sckkit-learn. So we just saw support vector machine. We just saw, now we're looking at the k nearest. So we're going to try to take in the parameter of n for neighbors. Yeah, the number of neighbors that it should query, like how many around you, if you want to do it this way. Well, let's do it this way first. If I just say for now, I'm going to say 1 neighbor. Okay, just find me the 1 nearest neighbor in order to use that to predict. So this is before when we said like, well, I'm in a sea of blue, but my nearest neighbor happens to be red. Let's see how well we perform. So we'll save that up. We'll go ahead and run the same thing as above. Python of banknote0.py. And it looks like on this one, just looking at one particular neighbor, we're able to correctly classify, well, most of them just incorrectly 1, which is pretty good. However, if we maybe try, sorry, my watch is going off. I'm going to try, though, bumping up the number maybe this time. Instead of using 1 neighbor, we'll try to do more of a k nearest neighbor approach. When we said, I look at the 3 nearest neighbors, shall we say, for instance, and see how well that performs. Well, in this case, well, check it out. So we seem to have gotten, bingo, 100% of the predictions correctly, as either described as authentic banknotes or counterfeit banknotes. So, and we could try these experiments again many, many times over because I'm just randomly reorganizing the data every time. So we're technically training these on slightly different data sets, and you might want to run multiple experiments on really just to see how they're going to perform. But in short, they all perform pretty well, like really, really well. And while some of them perform slightly better than others here, they might not be the case for every training set. So you can imagine like just beginning to test now very quickly by putting these machine learning models using SageMaker to be able to train on some training sets and then test on some training sets as well. Okay, this splitting into training groups and then testing groups and then testing so that Sckkit-learn has some functions built in for trying to do it too. Okay, so we just did this by hand now. I'm just looking at the time. I'm aware that it's probably burning energy at this point. Ankel, it's been a pleasure. Thank you for actually being so involved. I'm just going to tie up one last thing before we do cross up, which is to look at another function I have here of banknotes1, which is going to take advantage of another feature that still exists within Sckkit-learn, which we can simplify a lot of the logic down. Okay, so because all right, so there is another function that's built into Sckkit-learn called train test split, which is going to automatically split training data. Well, it's going to split your data into the test group and the testing group. So what I like to say here is the proportion of the testing group, something like 0.5, you know, half the data essentially inside the testing group. And then I can fit the model in and the training data on that, okay? And then I can make predictions on the testing data. So, and then just count up essentially, just compute how well we performed. So Sckkit-learn has some, again, nice math, just counting up how many times our testing data match the predictions, okay? How many times our testing data didn't match the predictions. So very quickly then can we start to write programs up with, I mean, albeit scary, but not that many lines of code. You know, it's maybe just like 40 lines of code here just to get through these predictions, you know, which then as a result, see how well we're able really to perform, how to do. So again, these are types of libraries now that can let us, without really knowing the implementation details too much, without really needing to know about the algorithms in a very practical way, just to be able to solve these kind of problems too. And so then that's with supervised learning, you know, the task of giving some data, some output, some like label data, some input output pairs to something. We would like then to learn some function that maps these inputs to said outputs, okay? Okay. And I'm thinking maybe I'm going to leave that for another time when we talk of reinforcement learning, maybe another time instead. Okay, well, the goal of reinforcement learning is just rather than being given the whole data set just from the beginning of the input-output pairs, reinforcement learning is learning from experience. Well done versus, you know, not very well done, etc., etc. Okay, and that's going to be great. That's going to be where we get agents to kind of physically, or in the case of that, virtually learn through environments. I think I'm going to say that for next time because it would be nice then to see that in practice when we start to use Deep Racer in AWS. So if I can get a chance to come on next week or some next time I do come on, we'll start to apply these principles, these techniques to Deep Racer so we can see how that works together. Reinforcement learning, exactly, where, yeah, this is the Pavlovian model. Rather than it being a dog and, you know, telling it off or doing a mess, we'd say, well done, you're getting through the track really quickly, or bad, you're crashing a lot, or bad, you're taking too much time, etc. So that's the balance we're trying to find with depth versus breadth-based learning. So we'll learn about that next time, I think. I'll put that. We'll put a pin on it for here so we can see this in more practical terms. But all in all, we're building up this model of machine learning and just, you know, it seems a bit theoretical, and to be fair, it is, but that's why we're here for, just exposing these things little by little. Okay, again, thank you so much for staying behind. I know these sessions are a little bit obtuse, but if you're happy to stay behind, ask them if you have any questions. As always, I will be happy to do that too. Otherwise, Nick, Mohammed, Chantel, Trudy, Dennis, Duan, Gareth, Isaac, Mohammed, Nick, Raymond, and Carlos, well, others who have just dropped off. Thank you very much for joining me this evening.